Okay, this is our introductory lecture on equilibrium. All right, so what is equilibrium? There are a couple different words, and one of the words is dynamic equilibrium. If the forward and reverse reactions are happening at the same rate, the reaction is said to be in equilibrium, or in that case, more specifically, dynamic equilibrium. When you're looking at a reaction that is in dynamic equilibrium, you will actually look at a reaction and think that the reaction has stopped. The reason you'll think the reaction has stopped is because the amount of reactants and the amount of products remain constant over time. However, upon closer inspection, you will find out that the reaction is actually continuing, but at the same rate, both forward and reverse. So at the point when something is in dynamic equilibrium, it means the concentrations of the A, the B, the C, and the D are not changing. They're constant. And we would see no difference in our reaction container, but the reactions are still occurring in both directions. So stuff is being produced, reactants are becoming products, and products are becoming reactants. It's important to point out that having a constant amount of reactants and products does not mean that the concentration of the reactants is equal to the concentration of the products. It just means that those concentrations are not changing. So if we want to simplify it a bit, we could say that the products, we've got two products. And if the reaction is in equilibrium, we could, as the products, have four. So I could have I could have two reactants, and I could have four products. So reactants, so this guy, he becomes a product, and this one, at the same rate, decomposes back to become a reactant. So reactants become products, and at the same rate, products decompose back to reactants, where at all the times I have two reactants and four products. You see, those numbers aren't equal. Being in equilibrium doesn't mean the amounts are equal. It means the concentrations are remaining equal. So chemists use a double-headed arrow to show that a reaction is reversible. So if we show that a reaction is in equilibrium, we would write the expression, for example, A plus B, and we've got this little reversible arrow here. There are three options to that. This is the one I typically use, the one that looks basically like a half arrow in each side. But it could be an arrow that has double heads on it or two full arrows. This is the least likely one that you'll see because it takes the most strokes, keystrokes, or hand strokes. So chemists use a double arrow to show that a reaction is at equilibrium. Okay? It's important that you remember that equilibrium means the rate of the reaction forward and reverse are equal. It doesn't mean there are equal amounts of reactants and products present at equilibrium. Of course, still our elements are all going to be balanced. I will have the same number all the time in a balanced equation of the number of sulfurs, but I'm talking about the concentrations. I'm not talking about the elements here. So equilibrium is dynamic if both the forward and reverse reactions continue, even though the reaction appears to have stopped, meaning the amounts are staying constant. Chemical equilibrium occurs when the number of particles becoming products is equal to the number of particles becoming reactants. So, based on the principles of equilibrium every chemical reaction is reversible. It's capable of moving in the forward direction and back. That's said in principle. In actuality, there are plenty of reactions that only can occur in the forward direction. For example, you can't unburn something. You can't unexplode something or unrot something. Those are all chemical reactions that you can't undo. But this is said in principle. In the principle of equilibrium, all reactions are reversible. So there's a Le Chatelier's principle, and his principle says, if stress is applied to a system in equilibrium, a system is going to change in a way that relieves the stress in order to reestablish equilibrium. So if we stress the system in some way, according to Le Chatelier's principle, it's going to want to regain its equilibrium, and it is going to shift in a way that's going to make it regain its equilibrium. So what are these factors that affect equilibrium? So one factor that affects equilibrium is the concentration. So if we change the concentration of either the reactants or the products, then the reaction is going to shift in a way to reestablish equilibrium. The next thing that would happen, that could affect equilibrium, is the temperature. If we increased or decreased the temperature of the system, that too would be a stress factor on the reaction, and the reaction would then act in a way to regain the equilibrium. The next thing is pressure. Now, pressure is only true for gases in a system. And so if you've got gases, then the reaction will readjust itself in order to reestablish the equilibrium of the system. What about a catalyst? Because in the last unit, we talked about the effects of things that affected the reaction rates, and catalyst was a thing that affected it. And here, it doesn't have any effect on the equilibrium. It will just make us get to our equilibrium point faster, okay? So the way I remember what to do when I'm faced with a change in one of my factors is I have two mnemonic tools for myself. One of them is the word touchdown, or TD. TD is the two sets of consonants that are together. And the other one are two vowels that are together. So the consonants go together toward the decrease, TD, toward decrease. And then the other two are vowels away from the increase, AI. So I say touchdown, artificial intelligence. Those are my two letters that go together, TD and AI. And that way I can always remember what is going to be the thing that writes your balance back to equilibrium. So let's give it a try. So we've got some reactants yielding products here. We've got some calcium carbonate, and it's yielding calcium oxide and carbon dioxide. And they're going to change the concentration. They're going to add some more reactants. Well, if you add more reactants, then this balance is going to be out of equilibrium. It's not equal anymore as far as in and out reaction, products and being formed and reactants being decomposed. So what does this reaction have to do in order to regain its equilibrium? Reactants are going to have to yield more products. So you gave me more reactants, I'm going to make more products, and my reaction will be back in equilibrium. Okay, so let's talk about our TDAI and apply it to what we're saying here. It's toward an increase. I'm sorry, it's toward a decrease. Sorry, I totally violated my rule. Toward a decrease and away from an increase. So what did we do? We increased this side. And what happened? It went away from our increase. So that's our AI. So toward a decrease, away from an increase. Here we increase the reactance, so the reaction shifts away from the increase. So if my arrow that we're shifting away is over pointed to the right, we would say this reaction shifts to the right. And we would say in favor of the, and what goes on the right? Products. So we would say this reaction shifts to the right in favor of the products. It would be a decrease in reactants and an increase in products. And that's what it has to do to reestablish equilibrium. All right, so let's give it another try, hopefully without me messing up my acronym. All right, so I'm going to increase reactants. If I increase reactants, what do we do for an increase? Away from an increase. So they're pointing that they've increased the reactants. That means I'm going to shift to the right in favor of the products. So I'm going to make more products. When you say in favor of the products, it means you're making more. You're increasing whichever way the arrow that you're pointing that makes your balance. All right, so what if I increase the products? Then this reaction is going to shift to the left in favor of the reactants because away from an increase, you increased again. So if you increase over here, the arrow gets pointed away from the increase. Okay, so what about if I decrease the reactant? What do you do for the D? Well, the letter that goes with the D is T. So that means it's going to go toward a decrease. So this reaction is going, and you're kind of drawing an arrow over top of your reaction arrow here. Okay, so this reaction is going to go toward the reactants. So it's going to shift to the left in favor of the reactants. So shift to the left in favor of the reactants. What would happen if I decreased the products? So once again, toward a decrease. So go to your reaction arrow because this is where you're going to make your decision of what's going to happen. And it's going to go toward a decrease, toward a decrease. So this would be the reaction shifts to the right in favor of the products. Okay. So remember, touchdown, TD, and AI, artificial intelligence. The consonant two letters that are consonants go together, and the two letters that are vowels go together. So toward the decrease, away from the increase. TD, AI. It'll work every single time. You just have to draw your arrow either toward or away over top of your reaction arrow. All right. So what about temperature? Now, temperature is just another guy on the seesaw as far as you're concerned. And in this problem here, they've given me the temperature. They've shown me that I've got 1,207.8 kilojoules of energy being released with this reaction. Keep in mind, this should be review that this is an exothermic reaction. How did I know this was exothermic? Because the number for the thermal energy always goes with whoever is lower down on your graph. So because it's with the products, that means that this is exothermic. So this temperature is just like any other guy on the seesaw. So we've got our little fulcrum here at the arrow, at the reaction arrow, and they're going to tell us what's going to happen to the temperature, whether it's going to be an increase in temperature or a decrease in temperature. So let's see what they're going to tell us. It's a decrease in temperature. So what are you going to do for a decrease? He's just like any other guy. So you go to the arrows, the reaction arrows, and you go toward a decrease. All right, that means this reaction is going to shift. Which way did you write this arrow? To the right. And so it's in favor of the, what's the arrow pointing to? The products. So this reaction with a decrease in temperature is going to shift to the right in favor of the products. All right, what if they weren't nice enough to tell me whether the reaction, now I see it says exothermic here, but what if they didn't tell me it was an exothermic reaction and they didn't give me the change in enthalpy in the problem? Then I really have to go back to what I know about thermal energy diagrams, and I have to remember that if I'm a negative change in enthalpy, then that means I'm exothermic. And if I'm exothermic, that means the temperature is with the products. So there's a little bit of review there that I'd have to know, that the exothermic reaction means that I'm getting heat released. All right, so let's see what they're going to ask me to do. They're asking me to increase the temperature. If I increase the temperature, I go to my reaction arrows. What do I do for an increase? I draw an arrow away from the side that's being increased. Okay, so that means that this reaction is going to shift to the left in favor of the reactants. So the reaction shifts to the left in favor of the reactants. Means you're going to make more reactants to make this reaction become equal again at equilibrium. What about an endothermic reaction? No different. The temperature is just another player on the seesaw. I get my question. It says you had a decrease in the temperature of an endothermic reaction. Go to your reaction arrow. What do you do for a decrease? Touchdown. You go toward a decrease. That means this reaction is going to shift to the left in favor of the, what's on the left here? The reactants. So your reaction would shift to the left in favor of the reactants. You would have a decrease in products and an increase in reactants. That's what it means when we say in favor of the reactants. Okay, they may not tell you the location of your temperature, so you will need to know the difference between your endo and exothermic equations. All right, so I've got an increase in the temperature. It's telling me I've increased the temperature. So what do you do for an increase? Go to the reaction arrow and draw an arrow away from what's being increased. This reaction will shift to the right in favor of the products. All right, now there's a slightly different story for things that are gases. First of all, if you're dealing with gases, everybody in your equation that you're talking about generally is going to be a gas. Or they could be things that all the other states of matter canceled out, only leaving gases. But everybody in your equation has to be a gas. The second thing is your equation has to be balanced. You see, they were kind enough here to provide you with coefficients. If they didn't, you'll need to balance your equation. Because for gases, you have to know which side of the equation has the lesser number of moles. So if you have an increase in pressure, the reaction is going to shift towards the side with the lesser number of moles of gas, okay? Because it's going to want to expand and be to the place where there is less moles of gas. So it's going to shift to the right in favor here of the reactants. The way I remember this is after I've balanced my equation, I use this tool to remember for myself. If I'm under a lot of pressure, somebody's yelling at me, I'm getting in trouble, I don't want to be around a whole bunch of people. So if I have my two reactions here, I've got my two sides of the reaction. This side of the reaction has two people on it. And this side of the reaction only has one guy on it. So which side do I want to be on? The side that has two or the side that has one? So the side over here has two and this side has 1 mole. And I always want to say, if I am being yelled at and I'm under a lot of pressure, I want to be alone. So there's no alone here because the lowest number of moles you can have is 1. So I would want to go towards this number 1. So I'm going to always go to the lower of the two numbers. That's if I have an increase in pressure. If I have a decrease in pressure, I say, oh wow, if I'm under no pressure whatsoever, I have a decrease in pressure, then I'm going to want to go to the party. So if there's no pressure, I have nothing on my plate and everything is footloose and fancy free, then I'm going to want to go to the side that has the greater number of moles. So when there's a decrease in pressure, I'm free and clear to go to the party, so I will go to the side that has the bigger number of moles. So a decrease in the pressure is it moves towards the larger number. So the way I remember that is there's no pressure, man. I want to go to the party. And so I'm going to go to the side that has the higher number for its coefficients. Now, sometimes there's more pieces. So if there's more parts to this equation, you're going to add up all of the coefficients. So there'll be a total number here and a total number there on that side, and it'll always be just of your gases. Okay, so go ahead and work on your practice problems and come back and watch this as many times as you need to. And if you have any questions, please be sure to post those on the discussion board of your teacher's Canvas page. Go to the discussion board and copy and paste whatever question you are having trouble with to your teacher's discussion board.